Welcome back to our video module on quantum mechanics. In our last video, we took a look at a potential energy profile with a well delta function. In particular, we're looking at what the waveform would look like with an energy that was below this potential zero, so to speak. But how would things change if we gave the system more energy? In other words, if we move the energy so it was above the potential at all times. Today, we'll be taking a closer look at the delta function potential well, with hopes of identifying how this situation is similar and different to the lower energy state. Now, if we follow the same logic that we did with the lower energy, all we need to do is modify our K value to be a plus 2me, because in this case our energy is always going to be relatively positive. We'll also change our overall form to a negative chi-squared psi, which means we're looking at an oscillatory solution. And if the form of this equation looks familiar, it should. In fact, this setup is not altogether different than what we saw up here with our free particle. Look at our energy in teal and our potential profile in gray, and you can see once again we have some sort of free particle with regions 1, 2, and 3 corresponding to varying energy differences. In a like manner, if we start off with what the form of solutions for this form of an equation, the general form of the solution for this equation looks something like this. And this mimics the types of things we saw in the free particle discussions, where e to the ikx indicates a wave moving to the right. E to the negative ikx is going to indicate a wave moving to the left. This is for x is less than 0, so in region 1. And then in region 2, you're going to have the same type of thing where c e to the ikx and d e to the negative ikx, accounting for waves moving in different directions in both zone 1 and 2. Well, what would this mean? Let's pretend for a moment that we start off with a traveling wave coming in this direction. This would be x is less than 0, and it's traveling to the right. So that's a e to the ikx. Now there's another traveling wave in the negative direction that's moving to the left. That would be like a traveling wave coming here, interacting in some capacity with the potential profile, and traveling to the left. Likewise, if we look at the right-hand region, we'll have a c e to the ikx. This would be the traveling wave that has continued through whatever disruptions occur with this potential profile. And finally, a d e to the negative ikx, which would be a traveling wave coming from the far right into this system, which doesn't really make sense from an intuitive perspective, because there's no reason to think that a wave's coming in from somewhere to become part of this system. That tells us that this d value needs to be 0. So to recap, we have some sort of wave coming in from the left, which we can express mathematically. From there, something happens around the delta function well, and we have some of that wave continuing through, some of the wave reflecting back. Finally, much of our equation closely mimics the free particle Schrodinger's equation, as well as the solutions here and here, conjuring up all of our discussions about a continuous wave frequency, our Fourier transforms, and the challenges of normalization for wave packets. But where things become interesting and different are where our potential profile becomes a delta function with some sort of reflection and some sort of transmittance of a traveling wave. Thank you for joining me in this little exploration of a potential profile looking like a delta function well when our energy is positive. I look forward to you joining me next time as we explore these coefficients A, B, and C, how they relate to transmittance and reflectance of these traveling waves, and what influence the potential delta well function has on these traveling waves. I'll see you then.